So we have trying to do interacting systems where molecules interact with each other, and we have done Mayer's theory, and Mayer's theory, which is gave rise to many other theories, but that is essentially theory of real gases and condensation. Something I forgot to tell is that this is also called, we did the reason of that it breaks down at high density, but it is more famous in physics. This subject is approached by chemists and physicists in a very different way. This is called high temperature expansion. The reason it is high temperature expansion, if you look at it, that the Mayer function A, which is e to the power minus beta ur minus 1. So when more temperature becomes large, beta becomes small, so f becomes small. So these kind of graphs that comes that becomes less important than these, and then these become less important than these. So at low density of gases, anyway this will be favored over this because there are not many molecules per unit volume, and these will be more favored than that. Probability will be larger, which will be picked up through the when you calculate the partition function, the cluster integrals and irreducible cluster integrals. But equally rigorous way of saying that the Mayer's theory essentially an high temperature expansion, and virial series is a series in density, but it can also be considered as high temperature because the higher virial coefficients rapidly decrease with temperature. So that's a different view which comes from e to the power beta u, and this high temperature expansion pervades all through statistical mechanics simply because of the Boltzmann factor e to the power minus beta. So the difficulty comes in statistical mechanics because of the interaction between particles, and we cannot evaluate the partition function, we cannot evaluate the total number of microscopic states, and that's why these few cases we can do rigorously plays a very, very important role, because they guide us and they provide us insight. Just like Mayer's theory went on to tell us what is a virial series and went on to develop many other things, like I told you, sol-gel transition, percolation, the clustering phenomena, the cooperativity, which is really, I explained, is a beautiful phenomena that you can have 10 intermediate size clusters, say in a particle you can have particle of 100, you can have 50 monomers and dimers, but other 50 particles can be distributed among the clusters which are 5 of say 10 particles. Now when you increase 1 or 2 more particles, these large particles can get connected because another particle can come in between. You can imagine it easily in a lattice, in a cell, that there are these clusters which are connected lattice sides, another big lattice sides, and then there is an empty between them. But as you increase the probability or the density, probability of finding a particle which is same as density, then that can get connected. So what happened in a very infinitesimal change, this 510 Mars can become 150 Mars. And suddenly these intermediate size clusters disappear from the system, and that's what happens when the rains. See, after rains, the clouds, all the things comes down and sky become clear, and you don't see any humidity beyond the point goes down, and everything, at least upper atmosphere. So this is the same thing, the cooperative. So that in that sense, Bayes' theory is a great theory and gave a lot of things, but it also has its limitations. As I said, that it cannot be pushed beyond the point where everything diverges, and I cannot extend to low temperature and high density. But with that caveat, we'll go ahead and do the next thing. So second interacting system, which of great use in statistical mechanics and find great use in phase transition, and because it is solvable in certain limits, it can be solved exactly. It plays perhaps the most important system in the entire physics of interactive physics and chemistry of interacting systems, and this is the Ising model. Ising model is a simple one-dimensional Ising model. It is also same thing is there for 2-dimension or 3-dimension, but they are equal 2-dimensional, 2D Ising, 3D Ising, but the original Ising is 1D. And then this is essentially, you have a one-dimensional chain or rod, and you have the spins, which are spins, or you can take them dipoles, whatever, and they are interacting with each other. So they can be parallel, anti-parallel, all possible. So the spins can be, so definition of Ising model is that it consists of spins. Spins can take only 2 directions. So let me write down the assumptions of the model. One, spins can be only up and down. And they are denoted by +1 and -1, as if one is the +1 and minus comes to a great extent from the logic that you have an external magnetic field. Because these are only for magnetic systems. You have an external, also it goes over for electrical systems. We use that in real dipoles. Okay, so now the spins can be up and down, and they are denoted by +1 and 1, and the variable that comes is sigma I, and sigma I can be +1 and -1. If it is +1 is up, and is -1 is down, and what I stopped telling in a minute ago, that why this is chosen, essentially because you have a field in mind and cos theta, and so up is the field is aligned on the top. That's just a nomenclature. You can do it any direction you want, but up and down cannot change in Ising model. So it's cos theta and cos pi. So +1 and -1. That's the logic of these two things. Then number 3, an important, very, very important thing, that I have only nearest neighbor interaction. Only nearest neighbor interaction. That means this spin here can interact only with this one and that one. Okay. So in a finite spin, when we want to finite chain, we want to do in order to reduce the effect of the boundary, we impose what is called a periodic boundary condition. That means we form a ring. So after that, it becomes this one. This periodic boundary condition, which is used in many areas of these chemistry computer simulations. Okay. That not a part of the assumption. The part of the assumption are these three. The spins can be only up and down, and so you do by plus and minus 1, and the only nearest neighbor interaction is taken into account. So given that, you would imagine that's a trivial thing to solve, but it turned out no. It's highly non-trivial. Nobody has been able to solve three-dimensional Ising model. There at one time there was sporadic claims of three-dimensional Ising model, but has not been able to do. Nobody, the three best people have tried. Nobody has been able to do. And the 2D Ising is exceedingly difficult, and still called the most difficult calculation in the history of physics. And that was done by Lars Onsager. So, the physical chemist. Very interesting. Now, so we go now, write down an Hamiltonian, what called Ising Hamiltonian. That you wrote down the other, the H equal to. Okay, let me write down the A1, then I general one. Okay, so I now spend some time on this. So this is a generalized version of Ising model, where the interaction depends on the location. That means this interaction can be different from this interaction. So if I call that 1, 2, 3, 4, 5, 6, then 1, 2 can be different from 2, 3, and this plays a very important role later, but we don't need it now. So we'll consider them to be constant and take it out. So J sigma is sigma J. Okay, so this done such that when these are both up or both down, then I get plus for both of them, and then it becomes minus, and that is favored, and that is called ferromagnetic interaction when parallel spins are favored. Similarly, -1, but however is a plus and minus, like in this case, or in this case you have 1 plus 1 minus, so that becomes minus 1, and this becomes plus, so that is not done. And now this is the magnetic field. So magnetic field, now if I again a matter of convention, these are all matter of convention, but they are perfectly general. You can change convention. If you don't like this convention, results will not change. So this is the magnetic field that is acting on it, which absorbs in it to combine the dipole moment or magnetic moment of the spin and the external electric field. That means a magnetic field is H, and then magnetic moment is mu, then B is H mu. So that is combined in that. The effect of the external field is important. Of course, you can have statistical mechanics in the absence of the external field also, which we'll do. But this is the major thing to know. This is the Ising Hamiltonian. This is a general Hamiltonian, valid for any dimension. You can have 2 dimension. You can again have spin up and down. Exactly same thing. The square lattice, the number of nearest neighbor, here is 2, it becomes 4. If you go to triangular lattice, then number of nearest neighbor becomes 6. Then you can go to FCC or BCC lattices, and which are just an historical comment that when you go to 3 dimension, you cannot solve it analytically, and you do fall back on a high temperature expansion, which is very similar to Mayer's. It's really interesting. And huge number of people till in 60s and 70s used to do these high temperature expansions of the 3-dimensional Ising spin. Very, very famous scientist, Dominic. Okay, So we have now defined the Ising Hamiltonian. And now I'll spend a little time telling you why such a simple Hamiltonian. It might not look so simple to you because if you are not used to kind of abstract things. So this is sum over I, and this is sum over given one configuration. This is, so I have 1, 2, 1, 3, or 2, 3, 2, just like we did in Mayer's theory. Okay. So this Ising Hamiltonian, I'll now spend a little time before I go to calculations to tell you what are the basic merits and certain things of this. Actually, what I have in notes is much better than written, but it is better than that. But let's see. This will do a little bit of the work that I intend to do. There's too much data here. Okay. So these are lattice models. So some of them analytical solution is possible. Okay. So this is the spin that I am talking. A chain of n spins, and this is the Hamiltonian, the Ising Hamiltonian, and you can understand now what is important thing to realize, that, and very important to realize, there are n spins. Now at any given instant or any given configuration, these spins are all having configuration which could be which is different from another configuration, but each configuration comes with an energy. So a given configuration, this Hamiltonian is for a given configuration. Okay. For example, let me consider this one. I will pick up a minus from here. Let's see, magnetic field is 0. I don't need it now. I would not need it for some time now. Now, I'll pick up a positive contribution from here, another positive, another, for some reason everything positive here. The person who do it is all antiferromagnetic kind of interaction. Okay. But if it were up, then as I say, so a given configuration comes with a given energy, which is exactly same we have in gas phase, that where at any given configuration, a number of particles are interacting with each other, and that configuration has an energy. And Boltzmann taught us that the weight of that configuration will be given by the energy of that configuration. And this is very essence of the statistical mechanics, how we build the thinking in statistical mechanics. Okay. So again, the Hamiltonian given, here one says what is ferromagnetic, what is antiferromagnetic, all these things. Okay. Now, how to do the partition function? Now in partition function, this Hamiltonian has to go in the numerator of the exponential, right? Minus this there in front of minus beta h. That minus takes care of the minus and minus here. I get positive. Now, the difference between the my earlier thing is that I have to add over all the configurations. So, so the sum over spins goes here in the exponential. But this is weight of a given configuration. But I have to sum over all possible configurations. So this is the same as in my classical or continuum statistical mechanics, the integrations over positions is the same as the sum over spins. There I take a configuration, particles are in the position R1, R2, R3, R4, Rn, and then I get an Hamiltonian for that. Then what I do? I integrate over all possible positions of the first particle, second particle, third particle, dr1, dr2, drn, which is exactly same thing we are doing here. We are taking over all, summing over all possible spins. But now you understand that it creates enormous number of configurations. Because each spin, though only can be up and down, it has a, if a number of spins are there, they are 2 to the power n. And if n is large number, like Avogadro number, then you have a huge number of configurations there. So the entropic part enters through all possible combinations and the Hamiltonian comes. Okay, so now the partition function is this thing. This we need not worry right now. Okay, so okay, now I want to there are going back. So the Ising models are explains properties of is particularly for Ising model, solids, polymers, micelles, reverse micelles. This simple thing is used rather extensively, and also the Ising model that we do is used for gas liquid transition, even condensation. You can have a Mayer's theory version of the Ising model or Ising model version of the Mayer's theory, and this is the one was part of PhD thesis. Okay, now what I'm going to do, I'm not going to do this difficult thing. I'll do something little simpler, and because it could become very difficult, and so I think I have explained that this particular spin comes with an energy. That energy goes to Boltzmann factor in exponential, and that gives the contribution to partition function of this particular configuration. This is not good. I think that's the one we discarded, right? Yeah. Okay. Now I'm going to consider only this part. I'm neglecting for simplicity now because I'll be able to do something. So this is now deleted. So I now have a partition function Un as a function of T, n number of spins at temperature T, sigma 1, sigma 2, sigma 3, sigma n, all the spins, then e to the power minus beta j sigma 1, sigma 2, sigma 2, sigma 3. So this is the partition function I need to evaluate with the condition that sigma 1, sigma 2 are they can take up and down.
It should be plus. You have plus beta.
Yeah, that should be plus. Thank you. So now, you notice the one thing that all these are coming as product. So I can introduce a composite variable sigma j c equal to sigma j minus 1 sigma j. Now let me see what are these composite variables will take. Now composite variables will be when this is plus, then minus, again plus, it is a plus, minus. So composite variable, while each of them have two variables, composite variable has four variables. Okay. So this quantity now, I can now write in terms of composite variables, which is right. Now, I can now calculate this contribution of, okay, this of course I have to do when j greater than equal to 2, because I have 1, 2, 2, 3 like that. So j goes from 2. So in this case j has to go from 2 to particle count. Okay. Now I have to do this composite variable. So now I write this as I bring the product outside and I take the sum inside. Sorry. This is my composite variable now. Sigma j c. Okay. Then e to the power beta j sigma j c. Alright. Now I can take each one j and let me calculate the composite variable. So now that will be e to the power beta j sigma composite variable c and sum over say jet speed. Then sigma jc has 4 values. So that will be e to the power plus beta j plus minus e to the power minus beta j. I have plus minus e to the power minus plus both minus. Then I have plus minus and minus plus. So that would now be 2 into e to the power beta j. It is beginning to take the character of, you'll see later, Ising model. So this is what I have done actually is equivalent to a factorization. I have factorized. I could factorize because of this form of, what I deleted, the form of that thing. So I have done a factorization, just the factorization you do. But that factorization suddenly gave me a wonderful form which now does not depend on j. Just the beauty. Then what I can do now? I can make this product here. So now I can replace now this by so many times the product, we got n minus 1, but n is very large, so I don't really care of that. So I have evaluated the partition function in the absence of a field of the Ising model. Let me do some work with that now. The way I always did was like this. This is the way I always decompose, factorize. That's the way I learned. But in the book that we have written is not like that, and that's a lacuna we have to really correct, because this is the way one should go. But most of the books jump into, probably Carson Huang has this way of doing things, because I remember that this is in many places the composite variable. But I'm unfortunately most of the places I looked into, they start with a very complicated transfer matrix, all these things, which is at least for us for physical chemistry background people is not a best way to start these things. Okay, now there's some extremely important thing coming out from there. Now free energy A, okay, that is then I'm just neglecting n is very large, so I'm putting that equal to n. I hope I'm doing all this right. Now, What is this quantity? E to the power beta j plus e to the minus beta j?
2 cos.
2 cos. Okay. So now again 2 to the power n. So then kbt, I have a there, so this term I want to write, take it out. So plus 2 in kbt ln2. Please check me if I am doing anything wrong. So these two cancels, right? These two cancels. So I am left with partition function now. The free energy, sorry. So in the absence of a magnetic field, I have obtained the free energy. I am obtained the partition function and the free energy. Now there is something very important here. This continues to be in the presence of a magnetic field. The important part here is that there are certain functions in mathematics which are called entire functions. Exponential is an entire function. Cos is an entire function. And what is an entire function? That has infinite number of derivatives and is continuous all through. That function is called an entire function. So this cos is an entire function. So it cannot show any discontinuity. If it does not show any discontinuity, it cannot show any phase transition. And this is one of the primary result of the theory of phase transition, is that you cannot have a phase transition in one dimension. So this is also called a beautiful theorem, Ascope-Mervin theorem, but we don't need to go into Ascope-Mervin theorem at all, at least not in this kind of rather preliminary things that we are doing. But it is important to know that these cannot show any singularity. So it cannot describe phase transition. I can calculate entropy, I can get a dA dt of that and get the entropy, right? I can get the specific heat. And then I can calculate the fluctuation in energy, specific heat, and then I can find those two are the same. All these things one can do. And people have done, because this is the one model which has been beaten to death. But important result here is that because of this kind of beautiful expression, nice, neat, analytical expression, that we do have a completely analytical function. So there was this gave rise to a lot of logic and a lot of controversy, that a little bit of history, that how statistical mechanics can at all describe a phase transition. That means since Boltzmann is exponential and exponential is an entire function, differentiable completely to all order, how come then a statistical mechanics which is in the form of the sum of the exponentials, as we have seen it here, sum of the exponentials can give rise to a singularity? That was a huge debate in for more than 2-3 decades, which was ultimately solved in a specific case by Unsager, but in a very general case, beautiful by C.N. Young and T.D. Lee, called Young-Lee theory, Lee-Young theory. Two very famous physicists who also did quark and parity violation, and they went on to get the Nobel Prize for that. But their another beautiful work was showing how, and they use the Ising model and use the Mayer's theory, actually more Mayer's theory than Ising model, to show that how singularity can evolve by doing a beautiful piece of complex analysis that we can do sometime. Okay, so this is with the in the absence of a magnetic field. In the presence of a magnetic field is a little bit difficult, so I'll not do it in the class, but I'll go through that little bit and then I'll give you the final result. It's not too important that we do it for the major course of the thing. Those of you who are interested, you can do it, and if you get stuck, you can come to me and I'll do it.